So hi everyone, welcome to our inaugural Gigabrains meeting reading group. I want to emphasize this is a reading group, not a seminar. We want the bar for people to not really present but drive meetings to be pretty low. If people feel like they have to prepare a polished presentation, they might be less inclined to volunteer or do so. This is really a reading group. So in that spirit, I'm going to drive the discussion today with some slides, but I'm hoping to make this as interactive as you drive me to. So without further ado, any questions, any comments? If not, I'll start right away. All right, so I'm going to drive a discussion around this paper, Bitcoin Clique. The paper introduces the construction of a commit chain for any restricted scripting blockchain, and the main example would be Bitcoin. And to do this, we actually need quite a bit of groundwork, which could be the seminar topic by itself, each one of these points. I'm going to go through it quickly, but in later meetings, we may go through papers that dive deeper into it. So first of all, I'm going to talk about the two main tools that Clique builds on. Without these tools, we won't be able to understand it. One is this cryptographic primitive that prevents a party from trying to cheat, trying to double cheat, trying to double spend, trying to sign twice, essentially a predefined message. The second one is covenants, or CTV. This is a proposal for improvements of Bitcoin, which is not yet approved, but is potentially, there's good probability that the community will eventually approve it. And both of these tools enable a commit chain, or an off-chain platform that settles on Bitcoin, but does a lot of preparation and batching off-chain, and that's what a commit chain is. And the new one is called Clique. All right. So what is the difference between commit chain and payment chain? So in commit chains, there's an operator or a network of operators. It could be distributed, it could be centralized, but it is not the main blockchain, where some preparation of transactions that need to commit are made off-chain, but they're not an authority, and they don't represent any power to commit until the result is posted on-chain. So the benefit, why would you do that? The benefit is that you could potentially benefit from batching off-chain. You can take a bunch of transactions and maybe save on fees, or maybe present them more compactly. You could potentially do some netting off-chain. So if I send a coin and it's sent back, and I send it and it's sent back, at the end of the day, we could submit only the net result. There may be privacy benefits in some commit chains. So a group of users are all transacting, and then they reflect the final result. And there may be compaction, both the compute and the storage, where what is stored and settled on chain is much more efficient than off chain. So these are the benefits. The drawbacks are that at the end of the day, until a commit chain settles the state on chain, it is not settled. So the users have to still post everything and settle on chain. And the other biggest drawback is that it represents a different trust setting. So the operator or operators of the off-chain need to have some degree of trust. So they're not trusted as the authority, but they are trusted, for example, to serve everybody fairly, to be up, to be reliable, all sorts of trust issues. Some examples, so Plasma was a state chain or a commit chain that was introduced for the Ethereum ecosystem. And still a lot of lobby behind it. Rollups are a different type of commit chains that emphasize the compactness. They generate a proof of the state, which is much more compact and much more easy to validate than the state itself. But again, the final authority is the chain. And this is very different from payment channels like Lightning and others, where payment channels generate an updated state of the channel off-chain, which never needs to be posted on-chain unless there's a dispute or unless you want to close the channel. So the parties always know that they have the power to exit, and they don't need, in theory, never need the main chain to settle. Why would you ever want a commit chain instead of a payment channel? Sounds like payment channels are advantageous. You never need to pay fees. You never need to post to the slow and costly and limited capacity chain. Well, the reason is that payment channels at this point, the solutions that we have are peer-to-peer, and so they require a lot of liquidity locked between every pair, and they don't allow payments between a large group of participants. And this is exactly what Clique is trying to solve and address. Comments, questions so far?
I think I'm good with the last slide. Yeah.
Awesome. Actually, I think I went through this slide already. So let me immediately switch to Clique. So the two tools which are needed to enable Clique are a new cryptographic or a semi-new, an enhancement of a known cryptographic primitive called two adapter signatures, or 2AS, and this new opcode which is being proposed for Bitcoin as the software called op check template verify, or op CTV. We'll just refer to it as CTV. Let me start with 2AS. And looking to see who is on the call. Okay, so in a nutshell, what 2AS, and I'm not going to go into the cryptography, we'll probably have another reading group going in depth into the mathematics of one of these schemes. But 2AS is one of a family of cryptographic primitives that does a really interesting thing. It generates a signature in sort of an atomic swap way. So there are two parties that jointly generate a signature such that one party is guaranteed that if the other party participates, then if it signs twice, if it participates twice, some secret will be exposed. Let me make this more concrete. So here is the diagram. So we have Alice, Bob, and some public, board for posting. Could be the blockchain, could be, doesn't matter. So long as something is published, that's what we care about. So Alice will pick a message that she's going to send Bob to pre-sign, and a secret. So big Y is going to be shared with Bob, and little y is somehow connected to big Y, but Alice keeps it a secret. So this could be Alice's signature on a message or something that she doesn't want to reveal and doesn't want to commit to yet. Okay. And then she's going to share big Y with Bob, and Bob, using his private secret key, so a normal signing key, you have a secret key and a public key, SK and PK, SK and PK. So he's gonna sign a message that they both want to get signed, M, using this public value or the shared value, big Y, and produce what is referred to as a pre-signature. So this is denoted here as sigma with tilde. And importantly, the pre-signature will not pass validation. So if somebody takes Bob's public key and the message Y, and asks, is sigma prime a signature of Bob on the message M, the verification will fail. It will not be a valid signature yet. So Bob is not committed yet, and Alice also is not committed yet because Y is still secret. Bob will return sigma prime to Alice. Alice, using this information, big Y, or anybody that sees sigma prime, can verify that this is a pre-signature. So they can look at sigma prime and M and verify that it's a valid pre-signature using Bob's secret key corresponding to his public key. So they can verify it's coming from Bob, but they cannot go to a court and say, here's Bob's signature on the message. Alice, and only somebody who knows the secret little while, can now adapt this signature. So this is a malleable signature. This is a modifiable signature. She modifies the pre-signatures and turns it into a signature by Bob. Okay, so Bob is intentionally giving Alice, or anybody that knows the secret Y, the power to transform his own signature, his own pre-signature, into a real signature. Okay, but now they are both kind of atomically and symmetrically committed. So Alice gets sigma, which is Bob's signature, but if she publishes it, then Y, little while, becomes exposed. So both Bob and Alice exchange something atomically. Bob gave his signature to Alice. If Alice uses it, if she publishes it, she sacrifices or discloses her secret Y. So actually, what I described now is one AS, and 2AS is built out of repetition of two of these things. So in order to construct 2AS, Bob and Alice are actually repeating it again, exactly the same exchange, but with another set of values, big Y, small y, another message, M2, and pre-signature and the signature. And now, if both signatures, if Alice publishes and exposes both signatures, sigma and sigma 2, then she publishes Bob's signature on it and exposes her own secrets. So anybody that sees this can extract Alice's signatures. And again, there's a 1AS version, and the 2AS version is just repeating it twice.
Sorry, Dahlia, so one quick question. So is this protocol, so this 2AS, is this trying to prevent Alice from being malicious or prevent Bob from being malicious? I'm a little bit confused.
Alice.
Okay.
So the way it's going to be used, just jumping ahead a little bit, is that Bob will be, so in our use case, Bob will be the commit chain operator, and Alice will be any one of the users of Clique. And then there are going to be two commitments to the pool of coins that all the users are using. And if in order to redeem my coins, I actually have a balance in this pool. In order to reveal my coin, I would need to get Bob's pre-signature and then adapt it in order to redeem my coins. If I do that once, I'm fine. But if I use it twice, and you will see there's actually a pool and a collateral. If I try to redeem twice from both the pool and the collateral protecting it, then my secret Y, this combination will be exposed.
I see. And my second question is this the same or similar primitive used by Babylon as well? For their slashing mechanism?
Very similar. So I propose that we dedicate one reading or meeting to it. There seem to be two types of these primitives. One is called DApps, double authentication prevention signatures, and one is adaptable signatures, AS.
Mm-hmm.
And they're slightly different. They serve a very similar purpose. I'm not sure exactly what the history of this is. I think we should, at some point, dedicate a session to it.
Mm-hmm. Okay. Thank you.
And I believe Babylon uses DApps. Which is which is a cryptographic primitive, I believe, coming out of Stanford cryptographers, and AS is coming out of TU.
I have a question. So the M should be the same as M2 or not in the protocol?
In the protocol, it's not identical, but it's predetermined. So it's going to be, so they have to agree on what M and M2 are in advance for the signatures to hold. They're preset. They don't have to be identical.
I see. But the Alice and Bob should make an agreement on the plain text of M and M2, right?
Yes.
I see. Yeah.
And they're not going to be identical. Again, just thinking ahead a little bit, what's going to happen is op is going to generate, again, a place to store the tokens and a collateral to secure them. And Alice can redeem one of them, but not both. So it's slightly different. It's a different address. It serves a very similar purpose, but it's not identical bit by bit. You'll see that in a second. This is all I'm going to say today about TAS, how you use it, not how it is constructed, not the math, because otherwise we would spend the whole time today on it. Okay?
I see. Got it. Thank you.
All right, let's jump to covenants. So what is covenants? So covenants is this new opcode proposed for Bitcoin that allows to constrain the future use of coins, not just who can spend them, who should witness to spend them, but also how they spend them. So technically, it allows to put constraints not on the input, not on who can spend, as the input, but also on what is the output transaction, how it is being spent. And those of you who know Bitcoin very well, understand it very well. I will spend 5 minutes to just quickly recap that. But before that, let me give an example to keep in your head when I'm explaining CTV. So what does CTV enable, for example? So here's the example in the paper. So they allow a two-tier wallet. So I want to store Bitcoins on the Bitcoin chain, but I want, and obviously a key secures my coins. But if I want to use a two-tier wallet where I have two keys, one is a hotkey that I have on my phone or on my app and I use all the time, but it may get compromised. And another is a cold key that I keep secure, in a safe or maybe in secure hardware or whatever. How do I do that with the CTV? So what I'm going to do is, I'm Alice here. I'm going to deposit my coins in a normal, UTXO transaction. So I'm depositing my one coin as an input, but I'm going to constrain the output not only to who can spend it, but also how. So how I'm going to, so I'm using CTV here to constrain the output. The only way I can spend my coin is to send it to this dash transaction. So the dash transaction didn't happen yet. It's not, on chain. This I have to post on chain. And this I will post when I actually want to pay, when I want to send you my coin. What I'm going to do is first, the only thing I can do is I can spend it using this transaction. And what this transaction does is it sends my coin to some address that can be spent only using this output transaction. What this output transaction says is there are two ways to spend my coin. One is using my cold key, K1, immediately, send it to any address that I want. And the other is using my hotkey, K2, also sending it, but it will be delayed. So I'm putting a time delay on it. So what happens is that when I want to send you my coin, I'm going to send it to this transaction. And if I didn't compromise my hotkey yet, then I'll immediately post a transaction that sends you my coin under some delay. So maybe wait 10 blocks. During these 10 blocks, if my key is compromised, I can revert this transaction by using my cold key. And also, if I happen to compromise my cold key, I can always recover it by sending it to this address and then using my cold key immediately. So this way I can protect my keys. And importantly, look, what I've constrained here is the only way I can spend my coin. Now, I could immediately, you might ask, why didn't Alice simply send her coins here and then wait to spend them in either of two ways? So she could do that, but then her coins are locked already. And they're already in this address. And that's the only way she can use them. And then the delay starts, being in effect right away. Instead, what she does is she posts this transaction. And only when she wants to use her coin and actually pay, then she creates this transaction and posts this. And now the timer starts ticking. So I don't have to do a delay of 1 year. I could do a very short delay when the payment is made. And that's enough to secure the payment. So this is the example. Keep it in your head when we go through, just quickly how CTV enables it. Any questions so far?
Actually, I have a question. So for CTV, my understanding is, could Bob, for example, create that dash transaction for Alice in that case?
Anybody could.
Yeah.
Yes.
Okay. Yeah.
Correct.
It's not
Yeah,
only
anybody
Alice who can.
Yes.
Yeah.
Yeah. That's actually a good point. By constraining the output here, you're allowing you're not concerned about your transaction except being used at the right time. Yeah. So you can give anybody your transaction. It's in any case the only transaction that you can allow.
I have another question here. What's the limitation of the future usage of the output? Let's say I could just limit that only Bob could use the input, or could I just limit that both Bob and Alice could use the output in the future, or let's say any people, or just set to, let's say 12 people in a committee could use the output? What's the functionality of the limitation?
Yeah, so the CTV is just like any opcode. You can combine it using the scripting language. So you could, for example, do something like, in order to spend the output, you need CTV, with some template, the hash of a template, and the public key of user one, and the multi-sig public key, of some other public key. Or you could say, I don't know, or here.
I see.
So you could do anything in this. So for example, this says it has to be spent using this template, but you also require somebody to sign it, either PK1 or the multi-sig multiplicator. You can do whatever you want to combine it, and you will see examples when we get there.
Yes. So to summarize, this CTVO operator is composable.
Yeah, it's an opcode. It's a soft fork. You put it in a script. It uses one of the unused Bitcoin opcodes, and you could put it in any output script, just like any opcode. And it's when validators validate the transaction, they apply it based on the input and any witnesses that are attached to the transaction. And if it passes the script, it passes the script.
I see. Okay, thank you.
Yep. This is maybe a good segue to spend 5 minutes on recalling what UTXO is and how CTV differs from it. So generally, UTXO is this model where every transaction is a coin transfer that has inputs and outputs. The input could be either a mint of a new coin or one of the outputs of a previous transfer in full and authorized by essentially the condition that was set by the previous transaction. And then the output will be, again, a set of conditions that encumber the output. So it's not really necessarily a recipient, we think of it, but it's really a condition for redeeming, which in a normal case could be a public key or could be something, any script. And a transaction has a set of inputs and a set of outputs. The inputs are consumed in full, and the outputs can distribute the total sum of the inputs in any way that they want. And then a block in the Bitcoin blockchain could be any number of transactions. So let's see. So, when we look at an output, what it has is an amount and an unlocking condition script. And an input is simply the consumption. There's no real input. What there is a reference to a previous output with a witness that satisfies the condition. And then, as I said, the transaction is one or more existing outputs consumed and creating a list of new outputs. The picture is worth 1,000 words. So this is what it looks like. This is the Bitcoin blockchain. And here's a transaction. It has one or more outputs. And what this output is simply an unlocking condition, a program that says, how can you unlock this output? And then sometime later in the blockchain, some transaction references as the input this output by adding some information. We call this information a witness. This is the, you can think of it as the signature or any other information which is used together with the unlocking condition. Together, this is the program and its input, and you just run this stack machine. And if it comes out true, then the input is enabled. So this is very different from Ethereum, of course, and this is how UTXO works. And what are the types of conditions that you can see? So it's anything that's enabled by the Bitcoin scripting language, but to give some, really, really common examples, it could constrain the output to be signed by a public key. Essentially, what this means is we are sending this coin to somebody who can sign with that public key. It's like sending that coin to somebody. It could be this somebody could be a multi-sig, so you need a multi-sig signature. The script could contain time locks, and time locks could be either relative to the block that they're being that they're referring to, or they could be absolute and use real time because the Bitcoin blockchain timestamps blocks. And now we have this new type of condition that you can set on the output. The output would be encumbered to be spent only using a template which is referred to in a hash by this CTV. So this is, why is this a fork? Why is this not allowed currently? So if you think about what I just said, this is the chain. There's an output condition which places some condition. So here is an example. A public key is required to sign the output. And then when you look at the input, there's this purple area, which is a witness of the input. And in this case, it will contain the signature. And now you apply this condition on the input. So it's like you apply the script on the witness which is given. But what you cannot put in all of this is the output. You can see there's no way to even reference the output. This is just encode the same thing. But what CTV changes, it allows you to specify in the unlocking condition a test that looks not only at the witness, but the entire output transaction. So here, what you apply this on is not just the witness. Maybe I should have used a different color, but actually the output here is applied to the test. So it simply allows you to test what is the output, and the test is only one type of test. You specify in advance a hash of the output transaction in full. You cannot look at specific fields of the output transaction or what's going on. It's a full template. That's what it allows to do. And to go back to kind of the example that we had before, the two-tier key, this is what Alice would put in order to protect her own coins. She would send them to an output that has as a condition on spending it a CTV on a transaction template, TX. And what this TX will look like is this. Okay, so the entire output will be subject to this transaction, which says either you have a signature by public key 1 and wait a delay, or you have a signature by public key 2 and you can spend it immediately. By the way, I think in my previous example, public key PK1 and PK2 were the opposite, if you remember. So what will happen is that now suppose that somebody, Bob or Alice, actually posts an output transaction that spends this coin. This output is constrained to be exactly this condition. This is the only output that can be, okay? So now there's a coin in this output, and the condition to spend it is this condition. You can spend this output with public key 1, waiting a delay, or you can spend it with public key 2. This is the only thing you can do with the previous output, and now somebody has actually sent it, and the clock starts ticking, okay? So now one of two things can happen. Somebody could post a transaction using secret key 1. So as soon as this is posted to the Bitcoin, it cannot be settled yet because it has a delay. So what will happen is either that becomes settled if nobody sends another output, or if Alice is concerned that public key 1 was compromised, she has time before the delay to post a transaction signed with her cold key, key 2. And that invalidates this one. You cannot, double spend the same output. Okay. Any questions about the example or about UTXO? This was a kind of a quick blitz recap of UTXO and how CTV would operate. So far, we didn't get to Clique, but now it should be relatively fast. I think we have formally only 10 minutes. Quick question, do people have to jump in 10 minutes or do we want to stay a little over? When I prepared this presentation, I knew we would probably need an hour to discuss.
Yeah, I think I'm flexible.
Anybody needs to jump off? All right, so let's go until it will be 10:30 California time. All right, so now we get to Clique. Now, what I want to talk about is the core magic. And in order to do that, all we need to do is discuss the case of 3 users and forget about scaling later. So just show how you can secure using the Clique trick for 3 users that already is beneficial compared to payment channels, because in payment channels, if you have 3 users and they want to move coins between them, you need to have 3 channels, one between each pair of them. So already you need to lock, 1 coin for each channel or 2 coins if they want to have bidirectional, and already have 3 transactions and all that. And we will show how to do all this with 1 transaction in Clique. I don't worry about scaling. That's just computer science. That's trivial. I'll mention it in one sentence in the end. All right. So how does Clique work for 3 users? So Clique creates a funding initialization, which is a transaction where Alice, Bob, and Carrie are sending their balances. To make it simple, each one of them is sending 1 coin into this transaction. And the transaction allows the off-chain commit, commit chain operator operators. It could be a single signature, it could be multiple ones or a multi-sig, we don't care. Let's just call it OP, it's the operator. So it allows the operator to spend, the pool of 3 coins. However, the only way the operator can spend the pool of 3 coins is by sending it to another transaction, which is going to send Alice, Bob, and Carrie their coins back, or after a delay, it can redeem the coins by itself. So the operator, after a delay, can modify the disbursement and can also take all the coins to itself. So by an operator's signature after a delay, it can do whatever it wants. Okay, so again, anything dashed is not posted yet. You don't actually post it because that will send the coins back to the users. But what you do is you constrain what op can do. It can, or anybody can decide to redeem their coins back by posting this transaction. And this is, of course, encumbered by CTV. You cannot constrain what the output will look like. You can only constrain, who can spend it. But if you want to constrain one form of redemption to be this transaction exactly, that's enabled by CTV. But there's also an or. This goes back to your question before, Hongbo. You can combine this. So here there's a CTV, here there is not. Here there's a simple time lock.
Yeah, got it.
Any questions so far? It's a bit confusing. I'll go through this again and again and again, and you'll see it. But ask me any questions as we go along. So the idea is to create, this process where this is the initial funding transaction. Every epoch, the operator can update the disbursement with another transaction that looks exactly the same, but has a different type of disbursement. So let me scroll forward for a second. If the epoch has passed, this delay has passed, and nobody has redeemed their coins, and nobody wants to exit the system and close the system, then operator will post a new disbursement. But what this disbursement will do is it will reflect any payments that were made. So for example, the new disbursement could be that Alice sent 1 coin to Bob. So now the new disbursement, the only way to redeem it is to send Alice 0, Bob 2, and Carrie 1. And so again, going back, the normal mode is that every epoch of time, the operator will post a new netting and batching of all the payments that happened, and wait another epoch and post another. In between these epochs, if there's something going bad, if the operator goes down, if it's suspected to be faulty, or if a user just wants to exit the system, they can always post the transaction that does not have any delay and cause everybody to exit with their latest balances. So any transactions, any payments that happen in between the epoch and collected by the op are lost. They're only settled at epoch times. Okay, and once they're settled, the previous one cannot be spent. You cannot double spend, the previous one. Okay, so again, this is not like payment channels. This is every period of time you have to post this to Bitcoin, and you have a trade-off. If you post very frequently, then users don't have to take a risk, but you pay more fees and, it's more costly. If you wait a long time in this epoch, then during this entire epoch, the users are at risk. But that's a commit chain. Now, what we all want to know is technically a little bit, how is this secured, right? So you noticed that, you notice that here, the user can exit and causes everybody to exit. But op is trusted here to post the latest disbursement. So that means op, the operator, the operator has to have the power to create any transaction that it wants here. So it has, a delayed, a power to post a delayed disbursement. Or in particular, it can abuse this power and take all the coins to itself. So in order to secure this, Clique proposes to do the following. It actually creates two of these chains, or two of these pools. The first one has all the user coins. The second one is a collateral by the operator itself. So the operator has to deposit a collateral, which is at least the sum of all the user coins, maybe even more, to really punish the operator if it's wrong. And the two chains advance roughly step by step, creating the same disbursement. So every square here or rectangle here looks the same. So this one sends Alice, Bob, and Carrie their coins back. So does this one. But it sends Alice, Bob, and Carrie the coins out of the collateral. This one sends Alice, Bob, and Carrie a slightly different disbursement. So does this one. But it sends those coins, whether it's 0, 2, and 1, out of the collateral, not out of their pool. And the trick is that these chains have staggering epochs. So what happens is that this epoch ends before this one, and then it continues like this. So if the operator cheats at the end of this epoch and steals some of the coins or publishes a disbursement which doesn't reflect other payments, then the users can exit here and confiscate, and get their coins back out of the collateral. And vice versa. If op takes back the collateral and forfeits his own collateral, then the users still have a chance during this time to exit and close the system. Questions so far?
I have a question. Which threshold is the actual secured threshold? Sorry. Let me find another statement. So the amount of staked coins from the operator should be just larger than the amount of the participants' coins, or the double of them?
Not double. So the idea is that, remember this transaction without delay can disperse, 1 for Alice, 1 for Bob, and 1 for Carrie. This one has a slightly different disbursement, 0 for Alice, 2 for Bob, and 1 for Carrie. And the idea is that, these transactions are exactly the same disbursement. So here, each one of these transactions create exactly the same disbursement. So you only need 3 coins here. You might add some, I don't know, some punishment. Maybe send 1 coin to charity or whatever. But you don't need double. Why? I mean, where's your head? So, again, this is a discussion, not a presentation.
Yeah,
why would you expect it to be double?
I assume that you have the operator has two chances to get the punishment. Oh no, sorry. I'm wrong. Yeah.
It does, but it's you're right. It does, but it is staggered. So if it steals here,
Yeah.
there's still a larger delay until it can steal here, and during this delay, the user can exit. So
Yeah.
this is why this is causing this. As soon as the operator cheats, there's enough time, presumably, for users to exit using the collateral, and vice versa. If the operator exits here, then this triggers this action. The user will exit. There's enough time until the next
Apple. Yeah.
Apple.
I see.
That's why it's staggered.
Yeah, got it.
Now,
got it.
it's also, it has the same vulnerability, or, it has the same dependence on being able to react, constantly watching, seeing if somebody, it's the same thing as payment.
About to monitor the
Yes.
the click. Yeah.
Yeah. So all of these payment networks have this vulnerability, and there needs to be a large ecosystem to secure them. But technically, this is how this is secured.
I see.
Got it.
So, quick question. So, Dahlia, if I understand correctly, so it's essentially, even though those you have two chain in parallel, but the operations of like those chain, they are kind of have to be like synchronized. Am I understand correct?
Staggered, synchronized, but staggered.
Okay.
Yeah. So what will happen, I guess, is
Maybe they will stipulate the block height for these transactions.
yeah, something like this. So I guess I'm trying to be fancy here. So I guess, this is the start. This is the initialization. Then after the first epoch, there's an update on the main chain with new balances, but this transaction, as Ted says, is either posted with a delay or not even posted, and intentionally staggered, but it reflects the same balance.
I see.
So there are no extra payments. It's just intentionally staggered in time. So this is staggering.
Maybe this is a naive question. So how do they handle like denial of service attack? In the sense of, let's say if one of the
none of these payment mechanisms, they're all vulnerable to denial of service, bribery.
Okay.
There are a lot of papers that talk about, well, I'm the operator, I have $1 million at stake here. I can go to the validators and say, if you delay, the transaction that reacts to my, if you delay the user exit, so that I can double my $1 million, I will pay you $500,000. There are a lot of papers that talk about it. Yeah, absolutely. All right, moving on. So now, wait, So now you should have asked me, okay, so this secures against a bad operator, but now it actually gives the user the opportunity to exit twice. So the operator is delayed, right? The operator has this delayed exit, which is staggered. And if the operator acts badly, the user responds. But what about the user? The user could exit anywhere it wants. It could exit here, but it could also exit here, not in response to the operator, but just because it has a non-delay exit allowed at any point. And the user has this advantage because it always can operate on the latest posted disbursement. So even though they're staggered, like this one and this one, we have slightly different disbursement, it's still more than zero. And it still, takes all of the collateral. And here is where the 2AS signatures come into play, and here's where they shine. Until now, we only used CTV. And now the idea is to secure this using these 2 adapter signatures. So the idea is that when the user exits from this disbursement transaction, they don't just sign and send the output to their own address. They're actually going to do a very similar trick. They're going to sign a transaction. They're going to post a transaction that sends the money encumbered by CTV to another address, and that address can be spent by themselves using after some delay, or it can be spent by the operator if it knows the user secret. And the trick is that if the user posts one of these, then the operator doesn't learn the secret. But if the user posts 2 of these, then the operator will learn the secret. They will send the money to this address, which keeps the money, but the operator can take it right away. So here it is in a little bit more detail. So again, remember, we're now back to the basic single square. Remember, this is a single step, which every epoch is posted. So this is one step. It takes, originally it took the inputs, and then every time it posts the same thing. And it has, this encumbered output that the users can use to exit, where it sends the money back to the users. However, it is now modified not to send the money directly to the users. Instead, it sends the money to a disbursement that requires a 2AS signature and sends the money to another unposted transaction. And this transaction can be redeemed by the user itself. Here, I only expanded one example, but Bob and Alice are the same. So Carrie can get her money if she posts this disbursement transaction, and then she uses a 2 adapter signatures with the operator's participation to redeem her own coins into a protected address that she can redeem after a delay, or the operator can redeem without a delay if it knows her secret. So if she does this once, she actually gets her coins after some delay. So she immediately cashes, the pool, or redeems the pool. So the pool doesn't exist anymore. And then every user has to take his own coins or her own coins using 2 adapter signatures with the operator's participation. And that sends it to an address, which again has 2 ways of spending, one which is delayed and the other is a secret. And so what will happen is that if they do it once, it's okay. If they do it twice, both on the collateral chain and on the actual pool, these 2AS signatures are set up such that if a user posts this transaction twice, then Bob will, the operator will learn the secret. And the secret is, of course, going to allow them, the operator, to redeem the user's coins. And so notice that each user does this separately. Each user, in order to redeem their coins, need to adapt the operator's signature and create and post this transaction for itself. So if Carrie cheats, but Alice doesn't, then only Carrie will forfeit her coins. And this is basically it. At this point, it's just a matter of scaling, which, as I said, I don't get into. It's just a tree of transactions. Standard computer science. So any questions, any discussion on this? In the 3 minutes we have left, or whatever.
So I actually have a question. So for the secret Y in this diagram, I think I'm still a bit confused about whether these are the same Y or different Ys. So if we go into a little bit details of how the two AIS to set up to enforce such atomic withdrawal, I think the strategy here is once Alice, say for example, try to withdraw from both, then the operator has the ability to redeem one side of these two to even that out, or it's like.
Yeah. So I'm glossing over some of the details here, but yeah. So these are two different Ys.
Okay, that's my understanding. Yeah.
They either both get revealed or neither one of them. Maybe I should have used Y2 here to be more precise. These transactions, so here, this encumberment says, you can spend it immediately if you know Y2 such that hash of Y2 is big Y2. And here, the script says hash of Y is big Y, or Y1 if you like, to be precise. However, the 2AS primitive is such that either both of them or none of them gets revealed. So it's not like if she posts this transaction, then Y1 is revealed. If she posts this transaction, Y2 is revealed. It's only if she posts both transactions, both of them get revealed.
So basically, Alice will be penalized in the process.
Yes.
Okay.
And by the way, the way this is done is the construction, the main primitive is AS, 1AS. 2AS is simply done by having the secrets Y1, so Y1 and Y2 are really encoded very simply as a pair, Y1, Y2, which is some Y XOR Y prime. And so 1AS reveals this Y, which is nothing, it's garbage.
Mm-hmm. The
other 1AS reveals this, which is also by itself garbage. Only if both 1ASs are, if Alice posts both of these transactions, which means that she took ops signature here on this output and adapted it using 1AS in order to create this signed transaction. So it will be the operator's signature, but it is adapted from what the operator gave her as a pre-signature. And then she posts this. Then the operator reveals, this Y prime, which has no value. If she takes the operator's pre-signature on this output, pre-2AS signature on this output, and adapts it in order to be able to post this. So she now has the operator's signature to create this signed transaction and post it. If she did that, then she reveals the other Y. And now the operator can take these two, XOR them, and actually get the secret.
I see.
So the delay for carry in this example has to be wisely picked, so there's no.
As usual. Yeah, as usual, the delay is the security that op has for his collateral. Yeah, we're essentially done. I just want to mention, in order to scale to more than 3 users, what the paper does is it creates, this initial transaction is very simple. It's encumbered to be spent, but such that it sends half the coins to this transaction and half the coins to this transaction. No time delay, no nothing. This is what it does if, this is the only way it can be spent. And then these transactions again send half to each transaction until you actually get to the leaves, which are the users. And so what I concentrated on intentionally was, this last part.
Yeah. Yeah, I actually have a question for the exit from the user. So say if I'm a DOS-like user, so basically I put my money in and then I say I want to exit for some reason, and they cannot prevent me from doing that. Well, that's basically disable the entire epoch for other users, or it's fine, they'll still, the operator can still work on the current epoch. Because if that's the case, then I can easily, prevent the system from doing useful work by exiting each time as a user.
Yeah, so this is the comment here. Yeah, so in the full system, there are a number of enhancements. One of them, there's a tree of spent transactions where every user is a leaf. That means the user needs to publish a path, a whole path in order to redeem. But now, as soon as this is spent, it is spent. But what if you're asking, what if the other users don't want to exit? Then the paper presents a protocol for them to take all of their balances and kind of not surprisingly send their balances, so you have A, B, C, D, E, all of them want to continue. So they send all of their balances to a new route in a collaborative process, and then they create, a healed route. All of these are a little bit clunky to operate in a practical setting. But the paper is a theoretical paper. It presents a solution. If you look at Lightning Network, it is very, very clunky as well. But it is out there and it's working. It's not working extremely well, but people are trying to make it. And it's just like any technology. There's some friction initially, and then you remove the friction. Yeah. It is a correct solution, with the right incentives and the right security mechanisms and the right availability and capacity. Yeah, that's all I wanted to show. I have to say the paper is. I'm pretty impressed. The paper is pretty dense. It took me a lot of time to understand the key magic, even without getting into the math of the 2AS itself, just accepting the primitive. So I think it's pretty impressive. Yeah. All in all.
Yeah, I'm pretty impressed by your presentations because it's a very dense paper. Yeah, everybody, let's give Dahlia the Prof.
All right, thank you.
Any last minute questions before we wrap up?
So I think it means one has to transfer all its funds to another every time because it's kind of a discrete solution.
What do you mean by discrete?
One has to for this binary tree, one has to transfer all the whole fund of a leaf node to another.
Exit
is that
from the screen here.
Sorry?
Yeah, I'm just trying to leave Zoom for my iPad show so we can have a discussion. There we go.
Sorry.
Okay, there we go. Yeah, can you repeat? Sorry.
Sorry. I mean, one has to transfer the fund of a leaf node. If it wants to transfer the fund of a leaf node, it has to transfer the whole leaf node fund. So this is a very discrete solution. And maybe for the moment, it cannot transfer a fund of a flexible amount. Is that true?
Yeah. So again, there are a lot of pragmatic enhancements that would need to make this a real system. But I think it's innovative enough that it's very impressive. Yeah, and they talk about it a little bit. You need to have different denominations, not just the same denominations everywhere. You need to You need to do a lot of things to make it work. Yeah.
Yeah, sure. My idea
Um,
is since any integer can be detached into a summation of power twos, is it possible to make a binary tree a segment tree-like structure? And each non-leaf node can be equipped with the logic of refounding as well.
So the leaves could have any denomination. In fact, after a single step already, the leaves don't have exactly the same amount of coins. The tree doesn't have to be binary. I actually showed an example with 3 children. So the basic building block works with any number of children. The downside is that if you have k children at the leaf level, you cannot heal the leaf. You can heal the rest of the tree, but you cannot heal the leaf. The leaf is gone. So the more users you put under the same branch, the more fate sharing you have. I don't know. I just thought that the basic building block, of updating a disbursement between a group of users, that's pretty neat, but needs a lot of work.
I think he's
It's a very neat
suggesting, maybe the tree doesn't have to be a full binary tree. It could, it's like an octal tree kind of thing. So you can
Yes.
then you can have different
Totally.
granularities. So because your leaf is not at the bottom.
Yeah, and they mention it in the discussion.
Yeah.